Welcome to the course Guide to Kubernetes Security Posture Management, or KSPM for short. In this course, we'll dive deep into the strategies and best practices for hardening Kubernetes clusters. We'll cover how to enhance your incident response capabilities and implement robust, defense-in-depth measures to protect your environments. Our primary objective is to equip you with the knowledge and tools necessary to safeguard your Kubernetes clusters against a wide range of security threats. Whether you're an administrator, a developer, or a security professional, this course will help you elevate your security posture. So let's get started on our journey to mastering Kubernetes security. Welcome, everyone. As we dive into our session today, we begin with an understanding of KSPM, Kubernetes Security Posture Management. So, what is KSPM? At its core, KSPM is a framework specifically designed for assessing and improving the security posture of Kubernetes clusters. This means it helps us to evaluate the current security status of our clusters, identify potential vulnerabilities, and implement measures to strengthen our defenses. The purpose of KSPM is multifaceted. 1. Protect against common attack vectors. By continuously monitoring and assessing our clusters, KSPM enables us to guard against frequent and sophisticated security threats. 2. Enhance incident response. When incidents do occur, a solid KSPM strategy ensures we have robust mechanisms in place for swift and effective response. 3. Ensure defense in depth. This principle involves creating multiple layers of security controls, ensuring that if one layer fails, others will continue to protect our infrastructure. As Bruce Schneier wisely put it, security is a process, not a product. This underscores the reality that maintaining security is an ongoing effort, not a one-time fix. Through KSPM, we can adopt a continuous, proactive approach to securing our Kubernetes environments, adapting to new threats as they emerge. Thank you. And let's delve deeper into how we can implement KSPM to protect our Kubernetes clusters effectively. Welcome back. In this module, we will delve into some fundamental hardening techniques, focusing on cyber hygiene practices. The goal here is to understand the importance of these techniques in defending against common attack vectors. Let's first address why these basic security practices are so important. Cyber hygiene refers to the preventative measures you can take to maintain the health of your system. By adhering to these practices, you create layers of defense that complicate an attacker's efforts to breach your system. Here are some key examples of these practices. 1. Secure the Kubernetes control plane. The control plane is essentially the brain of Kubernetes clusters, making decisions about scheduling, responding to events, and scaling your applications. If compromised, an attacker could gain control over all your containers, which is why securing it is absolutely critical. 2. Limit external access. Reducing the exposure of your system to outside networks minimizes potential entry points for attackers. Utilize firewalls, VPNs, and network policies to control access and ensure that only trusted traffic can reach your resources. 3. Use role-based access control, RBAC. Implementing RBAC helps to enforce the principle of least privilege. By granting the minimum permissions necessary to users and applications for their roles, we reduce the risk of a malicious or compromised entity gaining elevated privileges. Now let's move on to a question to test our understanding. Why is securing the control plane critical? As mentioned, the control plane orchestrates the operations of your Kubernetes cluster. It schedules workloads, manages the cluster's state, and monitors activity. If an attacker gains control over the control plane, they can potentially disrupt services, steal data, or even control your entire Kubernetes environment. Therefore, securing this component is non-negotiable. By employing these fundamental hardening techniques, you'll significantly fortify your system against the most common threat vectors, making it much more resilient to attacks. Welcome back to our course on Kubernetes security. In this module, we're focusing on common Kubernetes misconfigurations and their impacts. Slide 4. Common Kubernetes misconfigurations. Misconfigurations in Kubernetes can have serious consequences, leading to increased vulnerability and reduced security effectiveness. Let's dive into some specific examples. First, improper access controls can allow unauthorized users to perform actions that could compromise your cluster. Always ensure your roles and bindings are properly configured. Next, insecure API access can expose your Kubernetes API server to external threats. It's crucial to configure your API server securely, using appropriate authentication and authorization mechanisms. Lastly, inadequate logging can hinder your ability to detect and respond to security incidents. Make sure you have comprehensive logging in place and monitor those logs regularly. Now let's put this into practice. Our activity involves identifying common misconfigurations in a sample Kubernetes setup. Take a moment to review the setup and identify where it falls short in terms of security configurations. This exercise will help you understand how to spot and correct these misconfigurations in your own environments. Remember, securing your Kubernetes cluster is an ongoing process. Regularly review and update your configurations to stay ahead of potential threats. Let's move on to the activity. Welcome back to our course on cloud security. In this module, we're going to discuss how to secure the control plane in your cloud environment. Specifically, let's look at the critical steps you can take to ensure robust security. Slide 5. Securing the control plane. Securing the control plane is essential for protecting the management and operational aspects of your cloud infrastructure. Here's a simplified approach to doing this by breaking it down into 3 phases: crawl, walk, and run. 1. Crawl. Use a bastion host. The first step is to implement a bastion host. This is an intermediary server through which all administrative access to your cloud resources must pass. It's like a gateway, ensuring that only authenticated and authorized users can manage your instances or services. This method is fundamental but effective, adding an extra layer of security by isolating and controlling access points. 2. Walk. Use a cloud provider service like AWS System Manager. The next step up is to integrate native cloud provider services such as AWS System Manager, SSM. Unlike a bastion host, AWS System Manager allows you to manage your nodes without the need for them to have public IP addresses. It facilitates secure connections and operations directly within your cloud environment, reducing the attack surface and enhancing security with sophisticated monitoring and logging capabilities. 3. Run. Use an identity-aware proxy. For advanced security, consider implementing an identity-aware proxy, which dynamically grants access to users based on their identity and context, not just network parameters. This zero-trust approach ensures that even if a user's device is compromised, it wouldn't necessarily grant inappropriate access to your control plane. This method offers granular access controls and integrates well with your existing identity management systems. Example: AWS SSM for secure node connections without public IPs. To put this into perspective, using AWS SSM, as mentioned in the walk phase, allows your nodes to remain within a private subnet without requiring public IPs. This configuration significantly minimizes your exposure to the public internet and leverages managed services for patching, automating tasks, and maintaining compliance. By following this phased approach, you can progressively enhance the security posture of your control plane, providing robust governance and reducing potential vulnerabilities. And that wraps up our discussion on securing the control plane. In the next module, we'll dive deeper into specific tools and best practices to further fortify your cloud environment. Thank you for watching. Welcome back, everyone. Now let's dive into strengthening Kubernetes authentication, a critical aspect of securing your cluster. We're going to look at different techniques you can use, which we've categorized into crawl, walk, and run stages. Let's start with the crawl stage. At this level, it's simplest and often sufficient for smaller or less complex environments to use your cloud provider's native authentication mechanisms. Most cloud providers offer robust identity and access management systems that integrate seamlessly with Kubernetes. By leveraging these built-in solutions, you can secure your clusters without much additional overhead. Moving on to the walk stage, things get a bit more advanced. Here, we recommend implementing OpenID Connect, OIDC, for direct cluster authentication. OIDC enables you to authenticate users directly against an identity provider, IDP, like Google, Azure AD, or Okta. This provides a standardized and scalable way to manage identities across multiple clusters and services, enhancing both security and operational efficiency. Finally, at the run stage, we target the pinnacle of security with zero-trust architectures. In a zero-trust model, the underlying principle is to never trust, always verify. Regardless of where the request originates, every access attempt is thoroughly authenticated, authorized, and encrypted. This approach minimizes risks by assuming that threats potentially exist both inside and outside the network. Let's wrap it up with a profound quote from Forrester Research. Identity is the new perimeter. As traditional network perimeters dissolve, securing identities becomes paramount. Strong authentication is the foundational step towards building a resilient Kubernetes environment. Implement these techniques in the order that makes the most sense for your organization, and you'll be well on your way to a more secure Kubernetes deployment. Thank you, and let's continue to our next topic. Welcome back. On this slide, we're going to discuss best practices for enforcing the principle of least privilege using role-based access control, or RBAC. Let's start with the basics, or what we call crawl. Restrict privileged access to specific groups. This means that from the get-go, only certain groups or roles in your system should have elevated privileges. By segmenting access, you minimize the risk posed by any single user's account becoming compromised. Next, we move to the walk stage. Use lower privilege accounts for regular tasks. Here, we focus on ensuring users perform day-to-day operations with accounts that have limited permissions. This reduces potential damage from mistakes or exploits that may occur during regular activities. Administrators should only use high-privilege accounts when absolutely necessary. Finally, the run stage. Use break glass accounts for emergencies. These are special accounts that maintain high privileges but are locked away and only accessible in urgent emergency situations. Such accounts should have rigorous logging and monitoring to ensure they are used appropriately. In this activity, you'll apply these principles by configuring RBAC for a Kubernetes cluster. Here, you'll practice creating roles and bindings to define what actions users can perform, ensuring our Kubernetes environment operates under the principle of least privilege. By the end of this exercise, you'll not only solidify your understanding of RBAC, but you'll also build a foundation for secure and efficient access management in your Kubernetes clusters. Let's dive in and start configuring. Welcome back. Now let's delve into Slide 8, where we'll explore the concept of using GitOps for cluster management. GitOps fundamentally transforms how we manage and deploy applications, and it offers several compelling benefits. Firstly, let's touch on the benefits of GitOps. 1. Predictability. GitOps ensures consistent deployments. By defining your infrastructure and applications as code and storing them in Git, it promotes repeatable and reliable deployments. Each change is tracked through version control, making it easier to understand what changes were made and when. 2. Security. With GitOps, you greatly reduce manual intervention, which is a common source of errors and vulnerabilities. By automating deployments, you minimize the risk of human mistakes that could lead to security issues. Now, to implement GitOps effectively, we generally follow a three-step approach: crawl, walk, and run. In the initial stage, we typically run Helm upgrade jobs. This is more of a semi-automated way where you manually trigger the updates, but using version-controlled Helm charts to ensure that deployments are consistent across environments. Walk. Next, we upgrade to using a GitOps operator. These operators, such as Flux or Argo CD, automatically synchronize the state of your Kubernetes cluster with the state defined in your Git repository. The operator continuously monitors your repo for changes and applies them to your cluster, making the process more automated and seamless. Run. In the final stage, we aim to eliminate manual write access to the cluster. All changes must go through the GitOps workflow, meaning they are made in Git and then deployed automatically. This creates a highly secure and entirely automated environment where the cluster state is fully defined by the code in your version control system. To sum up, adopting GitOps can significantly enhance the predictability and security of your deployments, and following the crawl, walk, run approach allows for a smoother phased transition into a fully automated, GitOps-driven workflow. Now that we understand the what and why of GitOps, let's move forward and dive deeper into how you can implement these steps in your environments. Hello everyone, welcome back. In this part of our session, we're focusing on preventing container escapes, specifically how to minimize risks by limiting privileges. On our journey from crawl to run, our first step is to crawl, audit containers for root usage. When we audit our containers, we are essentially checking to see which containers are running as root. Why does this matter? Running as root within a container can be highly risky because if an attacker manages to escape the container, they may gain root access to the host system. Next, we move to enforce restrictions with an admissions controller. Admissions controllers allow us to put in place policies that prevent the launch of containers running as root. By enforcing such restrictions, we make sure that only containers with non-root users are allowed to run in our environment. Finally, in the run phase, we check privileges during CI/CD. This is about integrating privilege checks into our continuous integration and continuous deployment pipelines. By doing so, we ensure that every new container image or update is verified for proper user permissions before it is deployed. So why exactly does running containers as non-root improve security? Containers running as non-root mitigate the potential impact of a compromise. Even if an attacker manages to break out of the container, the non-root user privileges limit the damage they can do on the host system. This is a crucial layer of defense in depth. Remember, the principle of least privilege is a key tenet of security. By ensuring that containers run with only the permissions they absolutely need, we add significant barriers against potential attacks. Thank you for joining this segment on limiting privileges. Let's continue to the next slide, where we will explore further mechanisms to enhance container security. Hello everyone, and welcome back. Let's dive into slide 10, Enhanced Incident Response. We're going to discuss strategies that elevate your incident response to a whole new level. First up, cluster logging. This strategy involves collecting and aggregating logs from your entire cluster. Logs are invaluable when you're trying to diagnose issues, trace security incidents, or analyze system performance. By consolidating these logs, you gain comprehensive visibility into what's happening across your ecosystem, making it easier to spot anomalies and react promptly. Next, we have real-time monitoring. Deploying detection and response tools ensures that you can identify and react to threats as they occur. Real-time monitoring enables the continuous scrutiny of network traffic, system activities, and user behaviors. With this approach, you can catch potential threats early and initiate a rapid response, reducing the impact of any incident. Lastly, let's talk about admission controllers. These act as gatekeepers, enforcing security policies during the deployment phase. Before any container or application is deployed, an admission controller evaluates it against defined security policies. If anything looks off, the deployment can be automatically denied or flagged for review. This proactive measure ensures that security is baked into your deployment processes right from the start. Incorporating these three strategies, cluster logging, real-time monitoring, and admission controllers, into your incident response plan will significantly fortify your defense mechanisms and streamline your response actions. Thank you for your attention, and let's move on to the next slide. Welcome back. In this module, we're going to discuss how you can enable cluster logging for your Kubernetes environments. Let's dive right in with the steps to implement logging effectively. Firstly, we have the crawl phase. Here, you simply use Kubernetes' default logging capabilities. By default, Kubernetes writes logs to the local file system of the node running the container, which you can view using kubectl logs. This is a good starting point to understand basic logging. Next, we have the walk phase. In this stage, you need to deploy a logging agent. Logging agents such as FluentD, Logstash, or FluentBit can collect logs from the nodes and containers and then route them to a log storage backend. This helps in gathering logs from across your entire cluster, providing a more centralized approach to logging. Finally, we have the run phase. At this stage, your goal is to push logs to a SIEM, Security Information and Event Management solution. This is where you integrate with more advanced log management systems like the ELK stack, Elasticsearch, Logstash, and Kibana. The ELK stack allows for powerful log aggregation, storage, and detailed analysis. By pushing logs to these solutions, you gain the ability to perform complex queries, generate alerts, and create visual dashboards for monitoring and analyzing your logs. To summarize, we start by using Kubernetes default logging in the crawl phase, move on to deploying a logging agent in the walk phase, And finally, push logs to a sophisticated CM solution like the Elk stack in the run phase to gain comprehensive log management and analysis capabilities. Thank you for following along, and stay tuned as we dive deeper into configuring these logging solutions. Welcome, everyone. In this section, we'll delve into real-time monitoring and the various techniques you can use to maintain a robust cluster environment. Slide 12, Real-Time Monitoring. Here we categorize monitoring techniques into 3 progressive stages: crawl, walk, and run. 1. Crawl. This is your starting point. At this stage, you deploy detection tools with their default settings. Think of it as laying down the foundation for monitoring. It's simple but provides you with the initial visibility into your system's health and operational status. Walk. Once the basic setup is in place, it's time to fine-tune your detections. This means adjusting the settings to better match the specific needs and characteristics of your cluster. Tailoring these detections allows you to filter out noise and focus on what really matters, greatly improving the accuracy and relevance of the alerts you receive. Number 3, run. In the final stage, you move beyond passive monitoring to actively responding in real time. This involves leveraging your tuned detection tools to continuously monitor the system and take immediate action when anomalies are detected. This proactive approach ensures that issues can be addressed before they escalate into significant problems. Remember, as Gartner wisely put it, you can't protect what you can't see. This quote emphasizes the importance of visibility in security and monitoring. Without a clear view of your system's operations, protecting it effectively becomes almost impossible. By progressing through these stages, you can evolve your monitoring practice from basic visibility to a sophisticated, responsive system capable of guarding your cluster in real time. Welcome back. In this segment, we're going to discuss an important security mechanism in Kubernetes, the admission controller. Specifically, we'll go through the steps to effectively implement admission control in your cluster. Slide 13, Admission Controller for Security. Admission controllers are a crucial part of Kubernetes security strategy. They act as gatekeepers, intercepting requests to the Kubernetes API server prior to the persistence of the objects. This way, they can enforce policies or trigger actions like adding default labels or escalating privileges. Steps to implement admission control. We've broken down the implementation into 3 progressive steps: crawl, walk, and run. Let's dive into each. 1. Crawl. Deploy with default rules. Start simple by deploying the admission controller with default rules. These out-of-the-box rules cover basic security best practices without requiring much customization from you. This step will allow you to gain familiarity with how admission controllers interact with your cluster operations. 2. Walk. Scan existing workloads for compliance. Once the admission controller is in place, the next step is to audit your existing workloads. Here, you scan for compliance with your security policies. This helps in identifying any current security gaps or misconfigurations. Essentially, it's a basis for your security posture, ensuring that all existing workloads retroactively meet your standards. Number 3, run. Write custom rules and do dry runs. With the basic setup and initial scans complete, you're ready to enhance your security by writing custom admission controller rules. Tailor these rules to fit your specific security requirements. It's crucial to perform dry runs with these custom rules. A dry run will allow you to test the rules' effectiveness without enforcing them immediately, minimizing any disruption to your live environment. Activity. Configure an admission controller in a Kubernetes cluster. As a hands-on activity, we will configure an admission controller within a Kubernetes cluster. This will provide practical experience, cementing the concepts we've discussed. We'll create both default and custom rules and perform compliance scans. By the end of this exercise, you should feel confident implementing and managing admission controls. So let's gear up for securing our Kubernetes environment through effective admission control. Ready? Let's proceed. Welcome to Slide 14, where we delve into the concept of defense in depth and its practical implementation. Defense in depth is a strategy utilized to protect information and systems by deploying multiple layers of defense. The core idea is not to rely on a single security measure, but rather to combine various safeguards, creating a more resilient security posture. By the time an attacker breaches the outermost layer, they will face additional hurdles, significantly slowing down their progress. The ultimate goal of defense in depth is twofold. One, to make exploitation exceedingly difficult for adversaries, and two, to facilitate easier detection of malicious activity. By incorporating multiple layers of security, you increase the likelihood of catching an attacker in the act, whether through automated alerts or manual observation. Let's look at an example to flesh this out. Consider an environment where network segmentation is implemented alongside role-based access control, RBAC, and comprehensive logging. Network segmentation divides the network into distinct segments, limiting the spread of an attack within the network. RBAC ensures that users only have minimal access necessary to perform their duties, reducing the potential impact of a compromised account. Logging provides continuous monitoring and generates logs that are critical for identifying and responding to threats promptly. By combining these strategies, you enhance your ability to protect critical assets while making it cumbersome for attackers to move laterally within the system and remain undetected. Defense in depth is essential for robust security architecture, effectively turning potential security breaches into detectable and manageable events. Thank you. Now let's proceed to explore how to selectively apply these layers in different security scenarios. Sure, let's dive into slide 15, which focuses on protecting east-west traffic within your cloud infrastructure. A key technology we use for this purpose is a service mesh. Let's explore some of the core benefits it offers. First, encryption. With a service mesh, all internal traffic between services in your cluster can be encrypted. This enhances security by ensuring that even if a malicious actor intercepts the traffic, they can't decipher the data being transferred. Second, mutual authentication. This ensures that both the client and the server in every communication verify each other's identity. This is critical in preventing man-in-the-middle attacks and establishing a trustworthy network environment. To help you implement these benefits, we recommend a phased approach broken down into 3 steps. 1. Crawl. Start with basic deployment. Begin by setting up the service mesh to cover your entire service architecture. Here, the focus is on getting the infrastructure in place. 2. Walk. Once you have the base deployment running, it's time to collect and analyze logs. This will help you understand the traffic patterns and behaviors within your services. Logging is invaluable for identifying potential issues like traffic bottlenecks or security vulnerabilities. 3. Run. In this phase, you'll fully leverage the capabilities of your service mesh by restricting network connections per app or service. Here, you'll implement policies to ensure that services can only communicate with authorized counterparts, providing an additional layer of security. By following this structured approach, crawl, walk, run, you'll progressively build a robust and highly secure service infrastructure, effectively protecting your east-west traffic. All right, let's dive into slide 16, protecting configuration files. We're discussing some crucial steps to safeguard essential configuration files using varying levels of complexity. Hardening techniques. 1. Crawl. Manually harden files. At the basic level, you start by manually setting permissions and access controls. This step typically involves reviewing each configuration file and ensuring only the necessary users or processes have access. It's fundamental but essential work to lay a strong security foundation. 2. Walk. Use hardened node images. As we move to the next stage, we use hardened node images. These images come pre-configured with security best practices. By deploying these, we can consistently apply security measures across all systems, reducing the risk of human error and ensuring a more uniform security environment. 3. Run. Monitor for modification attempts. Finally, in the advanced phase, we implement monitoring to detect any unauthorized modification attempts. Tools and services can alert us to any changes, helping us to respond swiftly to potential breaches. Real-time monitoring ensures that we can mitigate issues before they escalate. Question: why is it important to restrict access to critical configuration files? Restricting access to critical configuration files is paramount because these files often contain sensitive information, like database credentials, API keys, and system settings. Unauthorized access could lead to system misconfigurations, data breaches, and potentially catastrophic security incidents. By tightly controlling who and what can access these files, we significantly lower the risk of these vulnerabilities being exploited. In summary, protecting configuration files is a multi-step process that evolves from manual hardening to using secure node images and finally to real-time monitoring. Each step enhances our security posture, making it harder for unauthorized users to compromise our systems. And that's a wrap for this slide. Any questions before we move on? Welcome to Slide 7, Conclusion. As we wrap up, let's quickly summarize what we've covered and outline the next steps you should take. Firstly, we discussed the importance of implementing fundamental hardening techniques. These are the base practices that help protect your Kubernetes clusters from common vulnerabilities and threats. Next, we emphasized the need to enhance your incident response capabilities. Being prepared to quickly and effectively respond to incidents can make a significant difference in minimizing impact and recovering faster. We also talked about applying defense-in-depth measures. This layered approach ensures that if one defense fails, additional layers of security are still in place to protect your environment. Looking ahead, here are the next steps you should take. 1. Apply these practices in your Kubernetes environments. Start by integrating these foundational security measures into your existing workflows. Make sure they are part of your everyday operations. 2. Continuously monitor and improve your security posture. Security is an ongoing process. Regularly review your practices, stay updated with the latest security developments, and make improvements where necessary. By following these guidelines, you're well on your way to maintaining a robust and secure Kubernetes environment. Thank you for joining this course, and I'm looking forward to seeing how you implement these strategies in your projects. Welcome back, everyone. Let's dive into our slide on references, specifically focusing on Kubernetes Security Posture Management, or KSPM. For those looking to deepen their understanding, I'm excited to direct you to an excellent resource, the Guide to Kubernetes Security Posture Management by Jimmy Mesta. It's a comprehensive article that breaks down the complexities of KSPM, providing practical insights and best practices to fortify your Kubernetes clusters. I highly recommend reading it to enhance your security posture management strategies. You can access the guide through the link provided here, the newstack.io to Kubernetes-security-posture-management KSPM-Kubernetes Security Posture Management TUT. Leveraging this guide will help you stay ahead in securing your Kubernetes environments efficiently and effectively. And that wraps up this slide. Make sure to check out the resource for an in-depth understanding.